kind of talk about the theory, and now we start to apply it. And when we talk about the triangles of trigonometry, you guys will see that the things that we learned nicely sort of transition into that. And you may also find out that there's some things that you've seen before. That's always a possibility with math. So, yeah, it's a good idea to take out a place that you can jot down a couple notes. Have a calculator handy. That will actually come into play shortly. Let's find out how the theory that you learn can start to transition into some application with trigonometry. And I'd just be sort of share with you for the next couple months, that's what will happen. We'll take the theory that we learned and we'll keep figuring out how it transitions into another application. And it'll take us all the way through October and even November as we keep looking at trigonometry. So I have a problem here. Don't copy this down. It honestly is not intended to copy down. For one reason, it's a problem that should kind of look familiar. And although I don't remember everybody's test, good chance that you got some part of this, if not all of it, right on the test. So we have a situation where you have a point and you have a theta. Okay, again, don't copy this down because I'm just kind of using this as a quick transition. You would already say, Ms. Naylor, okay, you're going to make a sketch where, of course, the point creates a triangle, an angle that creates a triangle. And so, again, a pretty common procedure here. So 12 and 9 become the sides, and you would go search for the hypotenuse. Don't search too far. Pythagorean theorem or a little bit of special triangles. This is a special triangle because embedded in 9 and 12 is a 3, 4, and then this one is a 5. It's just been pumped up by a factor of 3. But you've got your triangle. Now, I hope you realize that what we do with this, because you guys did it pretty well overall, is that you find like these trig values. And of course, sine is defined as y over r. Don't forget that. Cosine is x over r, tangent is y over x. So we've got these things called trig values. Now you're saying, I bet you're going to draw the unit circle, right? Actually, I'm not going to, but don't forget the unit circle would be like back here, and that's what these numbers represent. Even though they're written as fractions, they would also represent those decimals for that point. Actually, what I'd like to do is I'd like to do this. Now, if you were blinking or dozing off, did you see what happened there? We just removed the x and y axis. So if the x and y axis disappears, now what? Well, is the sine still 9/15? Is the cosine still 12/15, etc.? The answer is yes, okay, because the truth is that those definitions are ultimately based off of theta. Now, theta gave us x and y, but we still have the same triangle, we still have the same theta, and so we still have the same definitions. We just need maybe another way to describe the legs of the triangle. We need some words that might be a little more sort of normal, okay? And you've heard these words before, so we're sort of now saying, yes, we can start to use this because we've already said that the radius is the same as the hypotenuse. Now, when you talk about the side that is across from the angle, the side that's across from the angle, again, it was the letter y, but now that it's across from the angle, maybe we could call it the opposite. Have you sort of seen these words in a math context? Now, there's one missing word here, and it's the one that's beside the angle. Beside the angle. It's kind of a fancy word. If you use it in like a conversation, people think you're really smart. What's a way we can say that you're beside something? Beside. Go ahead, Grace. Adjacent. Now, I get a sense, and I saw some of you like, I feel like maybe this would be good to write down. Yeah, let me pause a little bit, take a look at what's up here. If there's something up here that would be helpful to you, I could understand. This might be something you do want to sketch out. This is how we can start to define a right triangle. And I totally understand. I actually almost expect that there's things up here that you feel like, yeah, I've kind of worked with this a little bit. But give yourself a little reminder. So you've got the hypotenuse. You've got the side opposite. And then you've got the side that's adjacent. And this will always work for right triangles. Forgive me, I forgot to put this up here, but it might also just kind of help you to start to get your notes a little organized. You can always title this. Now, if you did jot some things down from the screen, what about those three definitions? Okay, they actually become the most important thing because, well, we can still find the sine of theta, and it's still 9 over 15. But instead of calling it y over r, we can use these sort of new and improved words. So how about opposite over hypotenuse? Opposite over hypotenuse for the sine. And that probably is something good to also add to your notes. And maybe, again, you're saying you kind of heard that. But if you haven't heard that, sine will be opposite over hypotenuse. So cosine is still 12 over 15. But with the new language up here, we could say it's adjacent over hypotenuse. Adjacent over hypotenuse. And are you already thinking about the last one? The right way to kind of put the sides in a fraction would be opposite over adjacent. Opposite over adjacent. Now, what I hope that you're kind of experiencing here as we pause is not that you're saying, okay, yeah, I've done this before. I got this. I kind of expect that you've seen this and remember this from geometry. And if you're like, I don't know if I got this, we're still going to study it and review. But what I'd rather that you realize right now is like where these really came from. They didn't just come from, the teacher saying, this is what this is, this and this. They came from our theory of trigonometry. And so sine will still always be a y value. Of course, from the unit circle, cosine is an x value. But when you start to take that triangle and sort of make the x and y axis disappear and put some more sort of regular language to this, you do end up with these definitions. Okay, so this is really where sine, cosine, and tangent came from. In other words, these three definitions using opposite, adjacent, and hypotenuse. All right, that's what we're going to do now. Actually, we're going to sort of leave the land. We're going to leave the land of the x and y axis, and we're going to kind of move into just like a right triangle. And there's all kinds of things that we can do, which makes for lots of fun in the next couple weeks as we talk about right triangles. And, well, one of those things, again, will be that outdoor activity tomorrow. Now, normally what we do with triangles is we solve them, but the word solve isn't just there because, we're in math class. When you solve a triangle, that's code for finding all the sides and all the angles. And again, you can jot that down if you want to. You can just kind of read it. That's actually the same kind of language that you would have used in geometry, even though that was quite some time ago. So we're going to find all the parts of the triangle if we ask you to solve it. And honestly, what I find for most kids is, even if you've seen this before, is still being careful with opposite, adjacent, hypotenuse. So as one other kind of little practice, you can put this underneath what you wrote. You can just kind of practice it with me. But if I give you a right triangle, and maybe it's kind of positioned differently, who knows how it's positioned, but there's an angle, commonly thought of as theta. What you want to realize is that that angle dictates what's going to be opposite and adjacent. Okay. By the way, the right angle, and this, I know that you understand this, but the right angle dictates what's the hypotenuse. Usually there's not a big confusion about that. So we've got the hypotenuse, but let's just make sure that the side that is across from the angle, the side across, is always going to be your opposite. Okay, and then that means the side that's beside it, of course, is adjacent. All right, again, even though I know you've seen that, that still is kind of the number one issue with just getting problems right. So let's do a problem. Let's actually solve a problem. In this case, you'll find out quickly that what you have are sides and angles, which we also describe in a similar manner that you've done in the geometry class. But just remember that we typically call angles by capital letters in a polygon. And then the sides would be lowercase letters, but they kind of match up with the angles. So, of course, if angle C is right here, then side C would be across from it. Side B is across from angle B, and side A. So, again, I'm using a similar method that you would use in a geometry class. But let's say that you have angle A to be 49 degrees. Just kind of a little pretend there. And we'll say that side A is 7. Not too worried about the units, whether it's 7 feet or 7 miles, it doesn't matter. Okay, so kind of interesting that when you look this over that you really only have a couple givens. But when you have what's given up here, when you have an angle and a side, what you're going to want to do is you're going to want to pick the right trig function. Okay? This isn't anything magical that I made up, but it is just a way to make sure that you guys pick the trig function that uses what you know and then what you want to know. What do we mean that you know and that you want to know? Okay, well, I think everybody can tell that we know side A. Okay, side A. But do you realize that that is the side that is opposite? It's the side that's opposite your angle. Okay, and again, that's probably the most important thing to do, to decide that that is the opposite. Okay, you kind of, you need to know what is necessary for you to solve the problem, and I'm suggesting that do you need to write out these words? A lot of kids do. I'll be honest, I'm even doing it. So I'm going to write out that this side then is the adjacent. I'm just going to remind myself that this is the hypotenuse, even though that's pretty easy. But now that you have written out these words and you realize that you know A equals 7, what you really know is opposite. Okay, and then we just kind of have the question here, what do we want to know? Okay, well, the truth is we want to know anything else. So you just kind of have to make a decision. And you can decide right now to find side B, because obviously that's something that is unknown. And we could find side C. You could find either one. But if as a class we've decided to find side B, then we've decided to find the adjacent side. And so opposite and adjacent. Opposite and adjacent is the call, and the answer to that is tangent. You're going to use tangent. You're going to use tangent because, of course, that's the one that uses opposite and adjacent. And this is kind of fun. That's why kids do a nice job with it. All you got to do is plug in. And, of course, you're plugging in what you have. You're plugging in 49 degrees. You're plugging in 7. And you can always call adjacent side B just to kind of keep it organized. And then it's calculator time. Okay, now be careful. It's calculator time, but it's also a little bit of algebra time. What you kind of have there is an equation. Some people would solve that equation by cross-multiplying. Some people just kind of think about the algebra, but when it all shakes out, you're going to end up dividing the right way. And that's just another thing to be careful about. You should be thinking about taking 7 divided by. You should be thinking about taking 7 divided by the tangent of 49. Now remember, before you turn that calculator on, or maybe before you hit enter, were you in the right mode? Are you in degree mode? I will share with you that we'll be primarily in degrees, as that is a common way to measure an angle sort of in the real world. Radians is not the pretend world, but radians is a little more mathematical. So yeah, we'll be in degrees, and it looks like 609 should do the job. So what do you need? Again, I realize that there's definitely the possibility that you've seen a lot of this, but anything that's happened, are we okay with the division? Okay. How about side C? And just kind of a quick conversation here. Yes, you could find side C using the Pythagorean theorem. Okay, mathematically, there's nothing wrong with that. You have the 2 legs. You could do a squared plus b squared, and you get c squared. What you want to realize is that the Pythagorean theorem is going to end up using an answer that you found, and it is slightly rounded. Okay, it is slightly rounded. So what that means is that side C might end up being then slightly estimated or rounded. If you can, using trigonometry and using your original data, we could have a good argument here. It could be a little better. So if you can do that, you should. And so I'm just going to, for sake of argument here, say that if we want to use our given opposite and find the hypotenuse, once again, we have a trig function that uses those 2 words, opposite and hypotenuse. And the call goes to sine equaling opposite over hypotenuse. So we're going to use sine. Okay, because when we use sine, we're able to use the given angle of 49. We're able, once again, to use 7. And now we can solve for C. It looks like that you have to divide it again. Don't forget about the last angle. It's kind of gravy. It's supposed to be kind of easy, but if all the angles add up to 180 degrees, then a simple subtraction will give you that missing angle. Now, if it's kind of crossing your mind, you're saying, do I need to, show all this? Okay, let me just sort of help you to relax a little bit and say, you show what is necessary for you to get the answer. Well, I am going to require you to show the setup. Okay, you always show the setup that you plugged into. I think that that's a good idea anyway. And then after that, whatever it takes to get the answer. Most of the time, people just use their calculator. I do have a couple extra things on the board just to help you, but we're looking for the setup and then, of course, the answer. Now, that's what happens if you're given a side and an angle. Okay, you'll pick what you know and want to know. But what happens if I give you, well, let me show you, but what happens if I give you no angles, or to say it another way, just the sides? See, we can make a pretty natural, hopefully, transition to this. But what if I do something like this? And again, basically, I give you no angles and just some sides. All right, so we have side A equaling 21 and side C equaling 30. Now, you should be saying, Miss Nelly, you did give me an angle. Right, I gave you the right angle, okay? But here's the thing, you're never going to use the right angle in sine, cosine, or tangent. Just hear that again. If you ever find yourself putting 90 degrees in here for theta, okay, then you're not using right triangle trigonometry correctly. Again, you never use the right angle for theta. What you want to realize is that theta is always referring to one of the base angles. And that's kind of where this problem starts. And it's also where it ends. It's understanding that you just need to find and sort of start with one of these angles. Now, a lot of kids will find angle A just because it's alphabetical. But what if for some reason it was angle B that we needed? You realize that you could find either of these angles first. Okay, if we decide to find angle A, then that kind of creates the language, that kind of creates the sides. In other words, that makes this side now the opposite. And again, I find that this is kind of the only thing that gets a little sticky for kids. It's understanding, okay, I'm going to pick angle A just because I like it, but that means that this side's the opposite. And of course, this side here would be the adjacent. The hypotenuse, you know, is always across from the 90. Take a look at kind of what we have here. We have two things that we know. Okay, I did a little quick erase here. We have two things that we know. And so you want to pick the trig function that uses both of those. Okay, it's kind of the only thing you can do. Okay, so here we have opposite and hypotenuse. And so we make the call to sine. We're going to use sine. Now, when you plug into sine of theta, you should kind of quickly realize that the variable is obviously now the angle. So it's the sine of A equaling 21 over 30. Now, there's a little algebra that's required, and it's kind of one of those times where I'm confident that you'll be fine with this, but we actually kind of learn, like, what does this mean a little bit later. But I think it's a pretty easy thing that I can show you, and even, again, you might say, yeah, I kind of remember that. But I'll explain to you kind of what that means in a later date, and we'll understand a little more theory behind it. But in short, we need to cancel out sine. This is an algebra equation, and I want to get rid of sine. Now, to get rid of sine, I don't divide by sine, okay, because I'm not multiplying by sine. But I do its inverse. And literally, when you do the inverse sine, you will cancel the sine. And of course, since it's an algebra equation, you do the inverse to both sides. Okay, because you always, of course, do the same thing to both sides. So we end up with the inverse, we'll usually just say, the inverse of 21 over 30. Now, I told you the other day that button that was with sine is the inverse sine, and now is a good time to use it. So hit second sine or shift sine, but you want to do the inverse sine. And I always like to say that the answer even kind of looks right. I mean, it looks like an angle. You say, what wouldn't look like an angle? Well, it's some kind of strange value that's too big or too small. It might mean that your calculator was in radians. So when you do the inverse, we get a nice little 44 degrees here. Now, if you were going to find angle B, which you'll need to find, let's kind of all be honest with each other here. You already did the hard work. You already thought about opposites and adjacents and hypotenuse. So is there any reason that you can't use basic geometry? No, there's no reason you can't do that. You should be able to subtract your angles and get that missing. Do you remember if it's a supplement or a complement? We actually found the supplement, okay, because all the angles add up to 180. So we can find that missing supplement. We can just say that angle B equals 45. Here's the thing, though, just at least for the couple minutes that we're going to be talking about this in class. I want you to realize, okay, that had you decided to find angle B first, it's kind of an interesting, simple change here, okay? Because if I was going to find angle B first, this side would have been the opposite. This side would have been the adjacent. And so the only thing that really changes is the trig function. The trig function using adjacent and hypotenuse would have been cosine. And even when it goes to filling in the numbers are still the same. We still have 21 over 30. Okay, but just kind of want you to see that the only difference here is the trig function. And so when I do the cosine of 21 over 30, of course I get that same angle. Remember, if you're saying, so how do you want me to do it? I'm not that kind of teacher. You don't have to do it my way. I'm just showing you that you certainly could have gotten the answer with cosine. Okay, same answer. Do what you got to do to get 45.5 degrees. Speaking of answers, we have one more thing to find, right? Okay, it should be, again, pretty easy, but finding the missing side B, I would expect that you're going to use Pythagorean theorem, okay? You could use some trigonometry with sine, cosine, or tangent. But again, I just kind of want to give my stamp of approval that there's nothing wrong with making it easy. You can use Pythagorean theorem, but it is part of the problem. Even if it's not super exciting, it is part of the problem. Notice the work that I'm showing and then the work that I'm doing. I basically set up the problem, which is always required. You need to set up the problem. But I completely understand if you can do the algebra on your calculator, just be careful, subtract the right way, take the square root of 459 and get side B. When solving for an angle, you actually will pick the two sides that you know. It's kind of like, what else would you do? You're going to have to pick the two sides that you know. You always use an inverse. Actually, kind of forgot that I had this here, but I want to make sure that you see it. You always use an inverse. when solving for an angle. Okay, you always use an inverse. It's funny, that statement up there, you might be saying, yeah, that makes sense. That's pretty easy. We're actually going to come back to that when we get back into some more heavy-duty math. And so it won't be the last time that you hear this phrase. You always use an inverse solving for an angle. So it's not a bad thing to just kind of hear, especially when things start to get a little heavy-duty again. That'll be actually in October, but inverses always give you angles. Okay, so happy times, a little bit of right triangle trigonometry. Now, we're going to, after you guys practice this a little bit, which is the purpose of the homework, we're going to slide right into some applications of this. And that's why, again, tomorrow we have this outdoor activity opportunity. Okay, you guys will find out that it quickly slides into an application.